We're going to learn how to differentiate trigonometric functions. So, okay, we'll start with this example. Now, first, you're going to sketch the graph of sine x. So, we're going to draw the graph of sine x. So, 0 doesn't work. And then you got 1 and -1, 0. 2 pi, pi. That would be enough. Okay. Right, so you get a sine graph. And same, similarly, sketch the graph of cos. Right, sketch these two graphs. Right, sketch the graph of sine and cos. And the next, we're going to sketch the graph of the derivative of these graphs. So we do so by looking at the gradient. So we start with the first one. So the gradient, we start with the stationary point because these are easy, gradient 0. So that means it's going to be 0 here, 0 there, right? And also there. 0, gradient 0. Okay, all right. And then we'll look at the sign. This is positive, isn't it? Positive. This is negative, decreasing, and this is positive. So that means if it's positive gradient, the derivative will be positive. So you expect the graph somewhere here. And then this is negative, expect the graph somewhere here. And this is positive, so you get somewhere here. So having this information in mind, maybe the graph look like that. Yeah. So, and this graph, if you look at it, what does it look like? Cos look like the cos graph. So maybe dy dx is the cos graph. But we're not. But this is a way of illustrating why the derivative of sine is cos, but not a proof. So by looking at the derivative, we can be quite convinced that the derivative of sine is cos. And you can do the same thing with the other graph by finding the gradient. So noting that the stationary point are these places. So it will be here, here, here. Okay. So stationary point, note that is stationary at the beginning and stationary at the end. And then look at this, it's negative. This is positive. Right? Negative and then positive. So it's going to maybe look like negative first, below the x-axis, positive above the x-axis. So look at that. What graph does it look like? Negative sign, yeah. It will be negative. So now we can see the connection between the derivative and the graph. But this is not a proof. But we'll look at the formal proof later on. We can use this result to get the derivative of tan. Let's get the derivative of tan. To get the derivative of tan, we use the fact that tan can be written as sine x over cos x, which means I could use the quotient rule to differentiate tan. So I'm going to differentiate d over dx, sine over cos, using the quotient rule. Maybe I should rub this off so you can fit that. Okay, let's use the quotient rule. The quotient rule says that it's u dash v minus uv dash over v squared. So we write down the derivative. So the derivative of sine is cos x times by cos x. So it's u dash v minus uv dash. Okay, and then we'll continue. And then minus u, which is sine x, times by the derivative of cos, which is negative sine, all over cos squared. Okay, and then if we simplify it, we get cos square x plus sine square x over cos square x. And what's cos square plus sine square? It's 1. So we get 1 over cos square x. And because it's 1 over cos square x, I could write it as sec square x. Oh, sec square x. Okay, so derivative of tan x is sec square x. We can also find the derivative of sec x. So again, we're using the definition of sec is that sec is 1 over sine, or 1 over cos, which can be written as cos x to power -1. So we can just use the chain rule to differentiate sec x. All right, so let's use the chain rule. The chain rule say you bring the power down, subtract the power by 1. And then it times by the derivative of cos x, which we just found out to be negative sine x. And then you can simplify that. Oops, I could extend the page. Okay, plenty of space now. So we're going to simplify. So if we simplify it, that will become double negative positive. And then that can be written as sine x over cos square x, which can be simplified as sine x over cos x multiplied by 1 over cos x. And why do I do that? Because now this is just tan, and the second one is sec. So the derivative of sec x is tan x sec x. Okay, so we've got the derivative of all the 4 trigonometric functions. Okay, so if we go to the next page, we're going to do a formal proof. Because as you can see, this is not really a proof because this just give you a rough idea why the derivative of sine is cos, derivative of cos is negative sine. But it's not certain that the gradient is exactly 1, isn't it? We just assume that the graph somehow starts at 1. So we should look at the formal proof, and the proof is not examinable. So we'll do that by differentiating by first principle. Whenever we find a derivative of any new function, we always use differentiation by first principle. Just how we differentiate e to power x, we use differentiation by first principle. So let's write down the formula. F dash of x is the limit as h approaches 0, f of x plus h minus f of x over h. So we're going to use this formula in our proof. And we'll also need to use this formula, the compound angle formula. Let's write it down. Sine, which is on the formula sheet, sine x plus y equals to sine x cos y plus cos x sine y. And we also need this special limit that we just learned in this course, that the limit h approaches 0, sine x over x equal to 1. So we need to use all 3 results in order to prove the derivative of sine x. Now the proof of derivative of sine x, as you can see, cannot be done at 2-unit level because we don't know these two formulas. So in extension 1, you get to see why the derivative of sine is cos. Yep. Yeah, as well as this formula. That's extension 1. All right, okay. Let's continue. Okay, so we're going to differentiate sine x. Let's use the formula. So we're going to start off by writing f dash of x equals to the limit h approaches 0. Behaving h approaches 0. Okay, all right, so we're going to do f of x plus h. So we're going to write sine x plus h minus sine of x over h. Okay, and then we'll continue. We're going to use the compound angle formula to expand the top. So we're going to expand this into sine x cos h plus cos x sine h minus sine x over h. Like that. And then once we do that, we're going to split into two fractions. How do we split into two? So we have to do something. We have to do. Okay, so we have to group certain things together. I'm going to group these two together because they both have sine x. So I'll write sine x outside and then write cos h minus 1. So I take a common factor out. And then we add cos x sine h like that. Okay, once we do that, oh, I forgot there's another result I have to write down. There's a compound angle formula. We also need another formula. Forgot to do that. Okay. Yeah, I forgot. Sorry. Need to do another formula. So small again. Yeah, I forgot to say there's another formula you need. There's a double angle formula for cos, which is 2 cos square so cos 2x cos 2x equals to 1 minus 2 sine square x. Okay, we'll have to use this as well. Okay, so we're going to continue with our proof. Okay, now we can split into two things. So we're going to split the fraction into 2, sine x cos h minus 1 over h plus the limit h approaches 0 cos x sine h over h. So split into two fractions and two limits. And then I need to make some changes. Sine x, I'm going to make some changes. So this cos h, using the double angle formula, become 1 minus sine square h over 2, right? Hopefully you can see that. Minus 1. And then we'll continue plus limit h approaches 0 cos x sine h over h. Yeah. So what I did is this is just using this formula. So 2x, instead of 2x, I put x here, then this angle will be half of this one. Right, so that's why it becomes h over 2. And things get cancelled. Got more complicated than I thought. Okay, but anyway, we've got h approaches 0. Okay, so we've got sine x still multiplied by negative sine square h over 2 h plus the limit. Actually, the other one, I could write it on the outside. See, the cos x is not dependent on h, so I could write it on the outside and write the limit h approaches 0 sine h over h, right? And how about the other one? The other one, the same thing. Put the sine x and the negative outside, and put in h approaches 0 sine square h over 2 over h. Okay, and hopefully you can see this thing becomes 1. Becomes 1. Okay, and how about this first bit? The first bit will become something else. Let's see what would that be. So we get minus sine x times the limit h approaches 0 sine h over 2 over h times by the limit h approaches 0 sine h over 2. So I'm going to split the sine square into 2. And the key thing is that when you take this limit, that approaches 0, isn't it? Because as h approaches 0, sine of 0 is 0. And because that's 0, whatever that is, we know it's a number. Whatever that is, they all disappear. So it just becomes 0 plus cos x. So we proved that the derivative of sine is cos x. Okay. All right, so let me make the page a bit smaller so you can all see. Okay, so that's the proof. All right, the test one, the proof will not be examinable in the exam, just there for your reference. Okay. All right. Next, we're going to find the derivative of cos. So to do that, we'll have to extend the page. All right. Okay, let's extend. So we're going to look at the derivative of cos. So to differentiate cos, all we have to do is to change cos into sine, which is sine of pi over 2 sine of pi over 2 minus x. And if we differentiate that, we know derivative of sine is cos pi over 2 minus x. And then we times by the derivative of that using the chain rule, -1. So we got negative cos pi over 2 minus x. and negative cos, and this just becomes sine. So it becomes sine x. That's where we get the negative from. Negative comes from here. So the derivative of sine cos is negative sine. Yeah, so we use the formula cos x is sine of the complement. Then because we know a formula for differentiating sine, we get this, which becomes negative sine. Okay, done. Okay, so now go to the next page. So we see all four are now known. These are the four formulas. How about cosec and cot? These are not examinable in the tuner course, but we'll include it here for completeness. So these two formulas. So as you can see, when you differentiate cosec, the formula for differentiating cosec is very similar to differentiating sec x. You just have to change the sec to cosec, tan to cot. And there's an extra negative. And same for differentiating cot. It's very similar to tan. The answer is just cosec with an extra negative. Yeah. So every time you differentiate a function that has a c in front, it's always negative, right? See, every time there's a complement, there's a negative. Hopefully you can see that. Okay. Every time there's a complement, so cos is complement of sine, so that's a negative. And cosec is a complement of sec, there's a negative. Cot is a complement of tan, there's an extra negative. Okay, so these are the general formulas. So if I want to differentiate sine, I have to differentiate sine first, which you get cos, then differentiate the angle, which is the derivative of fx. These formulas can be found on the formula sheet. So we can see that on the third page of your formula sheet, you will see that you only get 3 formulas, not 4. You only get these ones. So these formulas on your formula sheet. So if we go back, you only get sine, cos, and tan. That's it. So our differentiation formula on the formula sheet are now all covered. So we've covered everything. And in the next lesson, we'll also be looking at the integral of sine and cos. That means the whole formula sheet is now complete. I think we'll cover everything. Okay, after we do the integral of sine, cos, and other things. Okay, we'll go back to this. So that's what's on the formula sheet. So only these ones are given. That's on the formula sheet. That's on the formula sheet. That's on the formula sheet. But not sec. So you should know sec off by heart. Only these 3 are on the formula sheet. Okay. All right. Let's do the derivative of cosec and cot. Why is the derivative of cosec and cot look like this? So what you do is we can use the same ideas when we differentiate cosec. It's same as differentiating sec, isn't it? Pi over 2 minus x. And when you differentiate sec, we know the rule becomes sec is sec and tan. It produces 2, but they both must have the same angle. And you can see where the negative come from the minus. So it times by the derivative of this. This is the chain rule. And then we can go back. So all these are complement, which becomes sec will become cosec x. This will become cot x. And then you got the extra negative outside. Okay. Same proof for cot. Similarly for cot x. Okay. Okay, after this, we're going to differentiate variety of functions. Okay, we'll now apply these formulas to differentiate. Remember, some of the formula are on the formula sheet. We'll start with the first one, differentiate 3 tan x. How do we do this? We just look at the formula sheet, so I'm going to refer to it. Tan x is sec squared, so we're going to go back. So we ignore the 3, just write 3 times by the derivative of tan. Derivative of tan is sec squared x. So the answer is 3 sec squared x. Okay. Next one. Let's do the next one. Differentiate. Differentiate sign is cos. But don't forget to differentiate 1/3 x, which you get 1/3. Okay. Plus the derivative of cos x, which is negative sin x. So the answer will become 1/3 cos 1/3 x minus 1/3 sin x. Okay, good. Try the next one. Y dash equal, again, ignore the 3, and then the sec will become sec, and then tan. That's the tricky one. And the 2x stays the same. And then you need to remember to multiply by the derivative of 2x. If you get times by 2. So your final answer will become 6 sec 2x tan 2x. Okay, good. Any question? Okay, let's move on to the next page. Some more harder ones. Okay, try these ones. Okay, so differentiate tan, you get sec squared, and whatever inside has to stay the same, right? And then remember to differentiate it. We're going to differentiate times by 2 e to the power 2x. Okay, diff. Oh, wrong button. Okay, so which will become 2. I usually like to write the small function in front, so it reads better. E to the power 2x, sec square e to the power 2x. Yeah. All right, how about the next one? What rule do we use? Particle, yeah, because we times 2 things together. So remember the rule, y dash is u dash v plus uv dash. Okay, so every topic where we do differentiation, we're going to revisit particle again, the quotient rule again. So hopefully by the time you've differentiated sine, cos, and tan, as well as exponential, you probably would have memorized them off by heart. Okay, so we're going to do 2x, differentiate, get 2x. We get 2x cos x plus x squared times negative sin x. So you get 2x cos x minus x squared sin x. All right, how about the next one? F. Again, particle. So you get sine, and then cos is actually we'll differentiate sine first. All right, so sine is cos x followed by cos x plus sine x times the derivative of cos is negative sine. And if we simplify that, you will get cos square x minus sine square x. Okay, good. You don't need to simplify further. You can leave it like that. Leave it there for it. Okay, next one, h, which cos 2x, but you don't need to simplify. You can leave it like that. Okay, let's move on. Next one, we can do quotient rule. Quotient, so differentiate the top, which is cos x, times 1 minus sine x, minus the top, differentiate the bottom, we get negative cos x, all over 1 minus sine x square. And you just need to expand things. Expand. And if we expand things, we get cos x minus cos x sine x. And then the double negative get cancelled. They get cancelled. You get positive instead, plus. So you end up getting cos x plus cos x sine x, all over 1 minus sine x all square. And you will see that things get cancelled, that these two get cancelled, and these two add up, become 2, and the denominator stays the same. All right, that's your final answer. All right, let's skip at h because we ran out of space and also ran out of time. So I'll just do I with you. Okay, to do I, what you need to do, I and h are very similar. So we'll just do I. So you just write it like this, sine x cubed like this. So now you know you have to use the chain rule. So y dash, you bring the 3 down like this. No change to the inside. And then you must differentiate sine x, which is cos x. That's it, done. And you just write, the answer will be 3 cos x sine square x. After this, we're going to find the equation of tangent to the curve, to the cos graph. So we're going to differentiate that. So what do we do is, we're going to differentiate y dash equal. To find the equation of tangent, so you get negative sine 2x times by 2. Like that. And then you substitute pi over 4 to get the gradient. So you get negative 2 sine 2 times pi over 4, which you need to simplify to become pi over 2. So you have to work out what sine pi over 2 is. And sine pi over 2 is sine 90 degree. 90 degree. No, wrong. So sine pi over 2. 1. Yeah, 1. So the gradient is at it's 1. So it's negative 2. Once you got the gradient, we can use the point gradient form to find the equation of tangent. Let's write down the formula. The point gradient form is y minus y1 equal to gradient x minus x1. I think we've got everything. So we continue y minus the y1, which is 0. M is -2, we just found out. And the rest we got x minus pi over 4. And you can simplify by expanding -2x plus pi over 2. That's the tangent. Okay, finally, we're going to look at some further example. How about what happens if I differentiate sine x degrees? So all the x we've been looking at, they are all in radian. So we're going to differentiate sine x degree. And to differentiate sine x degree, we just have to change x degree to radian. Let's see what we get. So we'll know x degree to radian, you just have to multiply by pi over 180 x. Okay, so that's x degree becomes pi over 180 x. Actually, it's not, so you just change the degree, change the radians. So therefore, if I want to change sine x degree, if I want to differentiate it, I just have to change that to sine of pi x over 180. And we'll know that to differentiate sine, we'll just write cos. So we just write cos x, cos of the angle, times by the derivative of the angle, derivative, diff, which is just pi over 180. We'll also note that this bit here is x degree, right? So that can be written as x cos x degree with the extra pi over 180 in front. That's the derivative of sine x degree. And we should find the gradient at 0. Let's find the gradient at 0. Okay, so how do we find the gradient at 0? We'll just have to substitute x equal to 0. The gradient will become pi over 180 times by cos 0. What's cos 0? 1. So if you do that on a calculator, what do you get? Let's work out on a calculator. So pi over 180 times by cos 0, which is 1. It's the gradient is very small, 0.017. Very small number. And we're going to interpret graphically. All right. Now compare with the gradient of sine x at x equal to 0. That's in radians. So if I differentiate that, I get cos x, isn't it? And if I substitute x equal to 0, what do we get? Gradient is cos 0 is 1. So the gradient is exactly 1, right? Gradient is 1. But why is the degree graph not gradient 1? Well, to make sense of this result, if we go back, because if it's in degree, if I try to draw the graph, this is 0 degree, 1 degree. Can you see it's going up very slowly? So 90 degree will be across the page, isn't it? So that's why the gradient is very small. Gradient, right? It's just very small. So that's why when you differentiate sine x degree, which is another reason why we don't differentiate in degree, because the graph will look very big horizontally. Whereas when it's in radian, the gradient is exactly 1. That's why we have radian. Yeah. I think we're done. One more page. One more. Not one more page. We're going to go back to do an estimation We haven't done this example. Now we can do it using Newton's method. Okay, let's write down the Newton's method. What's the Newton's method? On page 9. Newton's method says that we're going to get the first second approximation. To get the first second approximation, we need to do, which is on the formula sheet, x2 equal x1 minus f of x1 over f dash of x1. So if I want to solve this equation, what you need to do, sine x equal to x minus 1, we're going to move all x term to the other side. So sine x minus x plus 1 equal to 0. And then we're going to let this thing fx. Call this fx. And then we can differentiate to find f dash of x. So that's why I have to do that today, not yesterday, because we haven't learned the derivative of sine. It's cos. So we got derivative of sine is cos x. And after that, we're going to use the formula. So the formula says that we're going to use x equal to 2 as our first approximation. So x1 equal to 2. Okay, so we're going to use the formula to get the second approximation. x2, we're going to substitute 2 in, minus f of 2 over f dash of 2. And then use your calculator. 2 minus f of 2 is sine 2 minus 2 plus 1 over cos of 2 minus 1. Remember to use radian mode on your calculator. So let's press the button. So we got 2 minus fraction. Check it's in radian mode. It is. It's r sine 2 close bracket minus 2 plus 1 over cos 2 close bracket minus 1. Make sure you close this bracket, otherwise you get the wrong answer. Press equal, you'll get 1.935. 1.935. 3 decimal place. Is that right? No, 936. Oops. Approximately. Compared to our result earlier, is that good? What did we get last time using graphical? Yeah, 1.9, right? But took us a lot of trial and error. Whereas the Newton's method are very, very fast. Today you will do exercise 5. Anyone remember? 5.9 today. Good. Okay, have a good day. All right. How do I turn? Shit to the